Okay, welcome back. We are going to work on our last maneuver. So just check out. You need R for this, so just make sure your R is ready. This is MW14. Do you see it? Is it open? So before you get started, I just want to talk about it a little bit. Yeah, okay, it's firing up. Now you will find that I'll just show. Okay, if you look at the exercise, that's the usual vectors of the figure. But one thing you need to know is I do ask you to dichotomize the reading. Now, what do I mean by dichotomize? If you look at LDL, these are quantitative. You need to make a vector called LDL good. That's the only other thing you need to work on. Make a new vector. That means you add on to this LDL good, and that will be just zeros or ones depending on the person's LDL response. So if the person's LDL is below 100, then that will be a success that's healthy. You call that one. You understand what I'm trying to say? That's what I mean by dichotomizing. So you make a new categorical vector called LDL good, which is one or zero, depending on the person's LDL reading. If the person's LDL reading is uh, below 100, then that person has a healthy LDL that's stable. Is that okay? That's what I mean. So you need to make an additional vector that's like LDL, something like this. LDL good. And then you have C, then ones and zeros like that. That's what I need. All right. Okay, so you can get started on that one. Okay, I think most of you should be done with it. I will not take long. I just want to do a very quick run through of what I think are the most important things that you should know. First of all, the exam is similar in higher style to the written exam. So through those, um, you will need to understand R output. Of course, you don't run R in exam, but you need to give an output that you can. Okay, so let's quickly go through all the summaries that we have on our page. Okay. Well, not all of them. Some of the more basic ones I will let you look at. But basically, I think the important thing starts from you need to know. Okay, of course, you need to know way back when, you need to know how to form confidence intervals for difference in proportions. All right. Which I think most of you are pretty good at from what I've seen in the exam. Formulas here. Didn't we just ask for these multipliers in this group work that we've done? So just remember, proportion problems do not use statistics. But I think primarily what is most important is not really so much about the formulas. That's secondary. The most important thing is every time you see a stats problem, you need to know what scenario is it. Is it first of all a proportion problem, or is it a mean problem? So if it's a two proportion problem, what can I ask? Well, things like confidence interval. So just make sure you have these on your cheat sheet so that you know. Let's look at the most famous test of all of statistics, which is, oh no, that's not what I want to do. I want to go to chapter F. Okay, this one. Okay, so I think this test is the most important one in all of statistics. The two mean comparison, you should know how to do this. When you compare two means, the only thing I can ask you is, confidence interval for difference in means. And also make sure you know how to do it. This is something you must never forget. This is the most basic, the most popular confidence interval, I think, in all of statistics. Then what else? There's the paired test. So paired data, right? Paired data is actually a one mean problem in disguise, because what has happened is you have transformed the data to be looking at just the differences. You are essentially testing the same thing. You're looking for whether there's a mean difference. But the difference is the distribution that is used is based off a one mean formula because your data has been reduced to. Then we have our famous chi-square test. When do we use that? That one you do when you have data that form what's called a contingency table. So you need to know how to form the chi-square statistic for that. We did an exam on this actually. Exam 2 had this kind of question. So you need to know how to get the chi-square stat, what's the reference here. I mean, look at the summaries that we made, please. Again, this is a proportion problem because there are counts given to you. All right. Then we had chapter 9. And chapter 9, Moodle is just horribly slow. Okay, very, very slow. Okay. Chapter 9 is more than two means. And when you start comparing more than two means, you still essentially are interested potentially in forming confidence intervals between pairs of means. And you still use this formula to get that score. Basically, a chapter 9 problem multiple means has only one explanatory variable. It can have more than two levels. Right? Then we went on to more complicated things. All right. We started the road of basically looking at simple linear regression and things like that. So, simple linear regression is the model looks like what? Intercept. Okay, quantitative response, intercept, slope, and then one explanatory variable that's quantitative. That's what makes it regression. Quantitative explanatory variable. You need to know what the slope is. Simple linear regression is pretty intuitive. Intercept, what does it mean? Slope, what does it mean? How do you make confidence intervals for anything? You just use estimate plus minus multiplier times SE of that estimate. So you just use the information in the summary. You can test whether that variable is useful or not using the classic F test once again from the ANOVA table. The degree of freedom is always pretty easy. The total degree of freedom for any linear model is always one less number of observations. You always get the residual DF by subtraction. Don't learn rules. You know that every quantitative variable always yields a DF of. And this is true when you go to more complicated things and multiple linear regressions. Okay, so is that okay? So again, now that we have learned more complicated models, these things actually, you'll find is perfectly consistent. There's nothing new here actually, or there's no exception, right? It's not like English where there's many exceptions to rules. The spelling is not consistent. This is consistent. Okay, then we had the classical block design that we talked about. You have one factor of interest. You have some other factor of interest that's the blocking factor. And then you do need to know this, right? Or how do you find effect estimates? I hope this makes sense. If you want to look at the estimate of the effect of a certain level, you take that marginal, you subtract it in. So again, all these summaries are here to help you study and make a cheat sheet. And you can have three cheat sheets. So these are important things. Unless they are so intuitive to you, you don't need to have them on your sheet. But I think it's worthwhile having these things. First of all, I mean, what else can I ask? You want to know what I'm going to ask? Look at the problems that we worked on. Effects, confidence intervals, and then ANOVA table. Of course, is this clear? If a factor has I levels, then the DF is one less number of levels. We've done this, I think, 30 times already. And then, okay, so if you went to the interaction part, you have an interaction term. What is the DF for an interaction term? It is the if I had an interaction between factor 1 and factor 2, which is the next chapter, then the DF would be 1 for the interaction. There's a new one, no? If I had an interaction term, what would the DF be again? That's right. The product of the constituent parts of the interaction. Right? That's why I always say, use subtraction. Don't try to remember a formula. There's no point. This is consistent. Yes.
So it's just subtracting the two DFs from the different factors.
Yes. So what this means is all these should add up to n minus 1. So if, let's say, this is 3, this is 4, this is 17, then it's 17 minus 3 minus 4. That's what I mean by subtraction. It's as simple as that. Yes.
Sigma, 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 1 k minus 1 k squared.
Okay, what does this mean? This is basically how you find the SS resid for any linear model. It's not something I'm going to ask you to do in the exam. I don't mind telling you that. Because it's super tedious. You have to take every observation and subtract the prediction of it.
Yeah, that's tedious.
But does it make sense that that's why it's an unexplained?
Yeah.
Right, because it's what the model can't tell you. The model tells you up to y hat. What the model can't tell you is the difference between what you really saw and what happened. So it makes a lot of sense. And then don't forget the total, which again is something I'm not going to ask you because it's so tedious. The total SS is always everything you saw minus the grade. It's the model that doesn't have anything, just grand mean. The most basic, mindless problem, if you like, the one that doesn't involve anything. Okay. So I think I'm not going to go to interaction one. And Ankova model, we just came from that. So things that are more recent, I think, are Ankova model. Do you know how to do a prediction equation for Ankova? It involves two things. There's quantitative, there's categorical. If categorical, you need to know what the benchmark is. So if you're not that, then you just zero out everything else.
Okay, so ANOVA versus ANCOVA. Is it just that ANCOVA has a categorical variable, or what are like the other nuances that?
Okay, good. Can anyone tell me actually what is an ANOVA model? ANOVA model has explained. Okay, first of all, the response has to be quantitative. That makes it an ANOVA model. But what makes something an ANOVA model is that the explanatory variables are all
Categorical.
yes, categorical. What makes something an ANCOVA model?
Explanatory variables can be either categorical.
That's
or
right, either or. And in fact, actually, for it to be an ANCOVA model, there must be some categorical quantitative mix. What is a linear model where all the explanatory variables are quantitative? What is that called? Linear models where all the explanatory variables are quantitative.
Multiple linear regression.
Right, those are MLR regression. You see, these things. So I mean, these things don't help you analyze the data, but you need to know these terms because these things are thrown around when people talk about statistical. Regression is the term used when all the explanatory variables are quantitative. ANOVA is when all the explanatory variables are categorical with levels. ANCOVA is when there's a mix. And then finally, we just came from logistic regression. Logistic regression is like going way back to the response is categorical. In fact, for this class, it's not just categorical, binary. It's simpler. There are logistic regressions called multinomial logistic regressions where you can have a non-binary 3, 4, 5 levels, but categorical. Okay, we don't even go there in this class. In this class, it's always yes or no, just like the group work you just did. Are you having a healthy LDL or not? So it's binary. And logistic regression model, because this was the last thing we taught you, I didn't break them up into what if the explanatory variables are categorical? What if they are not? In the example you just did in Moodle work 14, didn't you have some things that were categorical? Diabetic status, you're either diabetic or not. Hypertension status, you're either hypertensive or not. But what was the other variable that was there? Wasn't it age? Yes, that's quantitative. So you can see that the logistic regression model is also very flexible. No one calls an ANCOVA logistic. They don't go so because logistic regression models are more esoteric. They're not so well known. So people didn't give specific names for the statuses of the explanatory variables in logistic regression. They just say logistic regression. So it could be anything. Logistic regression models can have right-hand side explanatory variables that are entirely categorical, entirely quantitative, or a mix. But you don't use the term ENCOVA. I guess if you really wanted to, you can say ENCOVA logistic, but no one does that. It's not a thing. It came later. Logistic regression models came later. They are not as famous, so people did not distinguish between them. But just know logistic regression, categorical, binary response. In the all those formulas that you just ran through, like the W statistic, how do you compare between them, AIC? So my advice to you is make sure you at least spend time looking at the summaries. There are a lot of models. This class is called what? Applied statistical models. Like, is that what this class is called? And the name changed, I think. Anyone? Oh, this is bad. I don't even know the name of the course. What is this course called? Statistical methods. So embarrassing. I don't even know the name of the course. Okay. But basically, this course used to be called applied statistical models because all models. So you need to know what model they're talking about. So just look at the summaries. The summaries were made by us together. So look at it, make sure you understand it. And also remember in the exams, don't give me generic formulas. Tell me the numbers that you're using. 5, 7. What is the DF? Don't say DF is n minus 1. Yeah, tell me what is that number. But you, okay, so, and this is an instruction on the exam, but I'll tell you now, the confidence interval construction and all that, you don't have to actually compute the interval. Just give me the skeleton of what, you know, the way we do it in class, A minus B plus, no, like, just show me the numbers that you would use. I'm not here to test whether you know how to calculate things, right? To just list systematically this minus this. Just give me the numbers. But don't give me generic formulas. Don't say y bar I dot dot. Okay, that doesn't help me because I don't know whether you know what you're doing. But you have to give me the number, but you don't have to calculate. All right. So that is all. I will see you for the exam. Uh, I, yeah, I. The exam is so early. There's no point. But I will be having office hours, but not before the exam. So if there's anything you want to ask, you can email me. I guess. All right. Okay. Don't forget, exam is not here. Exam is in our Thursday classroom, right?